Hello everyone, we just got done with a video showing how to do a graphical method to find a solution to an equation where we just plotted and looked where it crossed to zero. And that was also contained the direct or guess and check method, as we call it, where we just kind of entered in a number and saw if it equaled zero. If it didn't, enter in another number. And we can do that by simply looking at the point at which you go from a negative number to a positive number and then zoom in from there. That's very time consuming and not necessarily the most convenient, and it's fairly manual. Ideally, we would like for our function that we're entering in to give us the next guess so that we can kind of repeat this process. And so that is what we are talking about when we do the direct substitution method. In that case, instead of using in the graphical method where we said f of x is equal to 0, we're now going to redefine an expression so that the f of x is going to equal to x. In other words, we have an expression where we have a whole bunch of mess on one side of the equation and we have x on the other side, at least one x. And then we can just enter in a guess, let it output an x, and then that new x becomes our next guess. And then we'll plug it back into the equation and get a new answer. And hopefully, if everything goes well, this will give us and eventually go to the correct answer. So let's give an example of this. We can say x cubed minus 17x plus 12 is equal to 0. So we have a cubic equation. We can rewrite this so that x is on one side of the expression and you have all the other mess on the other side. So we can do that by simply pulling this x on the other side and dividing by 17, and we'll have that expression. So this will be x is equal to x cubed plus 12 all divided by 17. Oops, and I'm just going to fix this so that the expression makes sense. Okay, so now we can take this equation here and put an x, a guess value into this side, and then it'll output a new x that we can then use to feed back in. So we can create a column of guesses, and we can create a column of results. In this case, I'm just going to call this f of x is equal to x. Okay, so we have on this side I'll make a guess of 0.8, and then over here I will say x cubed plus 12 divided by 17, and we'll get an answer. And and hopefully we can look at the difference between these two numbers, and that as we enter in the next number and go into the next result, we should converge to an answer that is the right answer. So we can actually say that the next guess is going to equal to our previous answer, and then we'll just copy and paste this down and get the next answer. Copy and paste this down, we'll get that. So we can actually just copy and paste this whole thing down, and you'll notice it gets smaller and smaller and smaller, and our numbers converge to the correct answer. In this case, 0.7864. Wonderful. Now that's a great result. We know that this solution, if we put this value 0.72864 into x, and here, will equal 0. The problem is, you know that this is a cubic equation, meaning that there isn't just one solution. There's likely 3. Doesn't need to be, but let's check. Let's plot this and see what it looks like. So if we plot x and versus over here we'll say f of x, and this time this f of x is going to be of this expression here. So I'm going to say -5, and this is going to be this to the third minus 17 times this plus 12, and we can plot this. Let's go ahead and see what we get. Insert. We may need to add more data points, but we can do that in a second. Well, you get the trend here, and you can see right away we actually have 3 solutions, right? We have the 0.72864, which is here, but we have a solution somewhere here around 4 and someone here around -5. Well, we do know that depending on where we guess, we'll converge to different solutions. That's the nature of these equations. We have to be somewhat close to our answer to get to that right answer. So what happens if we say -5? Well, crud, it didn't converge, it blew up on us. What if we say 4? Or what if we say -4? Well, it didn't converge to this answer here. It converged way back over here. What if we said 5? Or 2? Again, it's converging to that one value here. If we said 5, it's converging, unfortunately not at all. It's going way up here, blowing up on us. And this, in a nutshell, is one of the biggest problems with the direct substitution method, is it is notoriously not well behaved. It can be used, it's very convenient and very simple, but unfortunately for the nature of most systems and approaches, it may not be the most convenient or may not be the most reliable. But when it does work, it's very useful. Interestingly enough, you'll see here in this expression, I'm going to go back to point 8, you'll notice it's going that we can have this happen by copying down and pasting, and you get a better and better answer. Interestingly enough, Excel actually lets you do this in a single cell if you'd really like to. You can actually turn on what we call iterative calculations. If you go to File and go down to Options and Formulas, you'll see over here it says Enable Iterative Calculations. Select that and you'll find that in this case here we can say an equation is equal to, and we're going to plug in this expression here. We're going to say x, but this time for x we're going to actually use the cell that we're in, C15. So it's going to refer to itself. We call that circular referencing, and most of the time Excel hates it, but when you're doing iterative calculations it's okay. So you're going to refer to itself, cubed plus 12 F2, let's fix this, divided by 17, and you'll notice in one fell swoop it has converged to the answer that we have gotten above. Very useful and convenient, but oftentimes it's another thing you might not want to leave enabled. So whenever you do use that, you can go ahead and turn it on and then go back and turn it off when you're done. You'll notice if I try to do a circular reference in Excel now, it's going to let you know it happens. I'll say OK, and it thinks it's OK, but it's just going to warn you because those tend to cause problems. So unless you're doing iterative solutions. So that is the approach to it, and I want to give one quick just overview as to the problem with this direct substitution approach, and that's based on this idea of what we call, it's actually been used in description in chaos theory, and the idea that these equations can become very well unbehaved. And a classic example of this is the quadratic equation. If you take a quadratic formula and rewrite it as following, where you have x is equal to x squared plus c, you can know here you'll have this solution set for x. Now, depending on the stability of x, and depending on the value of c, you can have actually several different results occurring. You can either have no solution if it's greater than 1/4. If it's between -3/4 and 1/4, the solution can be attractive or repulsive, and I'll show you what this means. You'll actually get one of two solutions unless you guess exactly right value. You can actually get a system where you actually get it never converges and it bounces back and forth between two values, or it can become even more complex. What does this look like? Well, if you have the c value down below and you plot all the values of x that you get as you cycle through, if your c value is out here, it's going to converge to a nice one number. But as it gets more negative in this domain here, it will bounce back and forth between two different answers. It will never give you just one or converge to just one answer. It will bounce back and forth. As it gets smaller, it will bounce back to between 4 numbers, and 8, 16, it becomes much more complex. And this is actually why we say it's one of the thoughts of chaos theory, is by just changing this one little parameter, you can get a highly irregular, almost chaotic output result on X, where every X that comes that you guessed, put in, and what comes back out will be some number, and it will almost look random after some point in time. But this is one of the challenges between the direct substitution method, and the whole reason why the Newton's method was developed, because it allowed us to converge on a solution more readily without and avoiding this noisy convergence problem. So in the next video, we'll talk more about the Newton's method for convergence.